Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RIW. This is podcast number 12 Alpha on BalUns, Ununs, and common mode chokes demystified. What you'll learn is what are BalUns, Ununs, and chokes, what are they good for, how they work, how to specify the right one, how to build and test them, what a good one looks like and behaves like, and where and how to use them in an antenna system. So let's start with a little terminology. The common mode current choke, or CMC for short, forces a differential mode current and does not change the impedance from the input to the output, whereas a transmission line transformer, or TLT, can be any impedance conditioning device for impedance matching. Could be an autotuner, could be a tuned stub network, or could be a BalUn or an Unun. So let's talk about BalUns and Ununs. Well, they minimize the current imbalance between a balanced and an unbalanced device, and it may also change the impedance from the input to the output. And just a note, impedance ratios are given from the antenna side to the feed line side. So an X to 1, 4 to 1, 9 to 1, 49 to 1, whatever, is a down conversion from the antenna to the feed line side. So let's talk about common mode chokes, or CMCs. Here's a picture of the common mode current choke pointer here, and show you this is the two sides of a dipole, and the one side, in this case the left side, is connected to the center core of a coax, whereas the right side of the dipole is connected to the shield. Pretty typical. Now, in pure differential current, the inward flowing current would equal the outward flowing current exactly, and you then have a balanced system with no common mode. However, if there's any reason for an imbalance, whether it's because these two sides of the dipole arms are slightly different length, or have a different impedance for some reason, they have something attached to it or closer to a ground than the other one, a variety of reasons, it can generate common mode current which runs down the outside of the shield in what's called skin effect. And that can often happen when connecting unbalanced coax to a balanced dipole. It can generate currents that are often generated by imbalances between the two sides of an antenna, and they can be thought of as a third conductor in the feed line, primarily on the coax. So what is this common mode current anyway? It's unequal currents on an antenna or a feed line, often due to an imbalance in the two sides of an antenna. The current moves on the outside of the coax shield, creating a sort of a third wire. Often causes higher SWR at resonance than normal. Makes feed line a part of the radiating elements, makes the feed line susceptible to nearby ground effects, reflects current back into the rig and the microphone, and that's what's called mic bite, and can cause RFI in the neighborhood. So how do we measure it? Here's an MFJ 854 current meter, and it has a clamp-on ferrite here, and you clamp that onto your coax, and it is an inductive pickup that senses the net current on the coax. If you have pure differential mode, you'll have no common mode, and the meter will read 0. You can adjust the length of the one side or the other in the antenna to minimize the current on the outside of the coax shield, and often get a better SWR. Helps you tune the antenna, helps you balance it better. Even if the overall length is perfect, your feed point may effectively not be quite in the middle. So let's talk about chokes. No, not that kind of choke, but the one-to-one current choke, also known as the RF isolator or line isolator. You'll always notice it as a transformer that's laying down. Here's the center pin of your coax coming in, center pin of your coax going out, ground braid coming in, ground braid coming out, and almost always uses mixed 31 ferrites. So common mode current chokes, or CMCs, can be toroidal ferrites, they can be snap-on ferrites, or even a coax air coil. For the ones that use ferrites, they almost always use mix 31 for best performance. If it's placed near where the feed line meets the antenna, it keeps the coax shield from becoming part of the antenna system and prevents RF in the shack from biting you. If it's placed where the transmitter meets the feed line, it reduces pickup of local RFI into your receiver, and when end-fed half-wave antennas are used, it could act as the counterpoise for your end-fed half-wave. The input and the output are interchangeable. It's a one-to-one relationship. They do not perform any impedance transformations, and they can even be helpful with ladder line. So let's take a look at a very popular CMC. It's the inline coax wound one-to-one CMC. The crossover here suppresses self-resonance, is what they say. But really, in practicality, all it does is it lets you bring the incoming coax and the outgoing coax on opposite sides, making it easier to use on an inline kind of a configuration. About 5 to 7 turns of each half. You don't even have to take off the PL259 connector. You can pass that through an FT240 31 mix ferrite and build one of these in about 5-10 minutes. And the ferrite costs about $10. And the coax you probably already have. A 3-foot piece of coax works just fine as pigtails with PL259s already on the end. Now, if you want to wind a CMC, here's a couple examples. You can do a bifilar wind or a split wind. Okay, so here's bifilar all the way around, and here's split on one side and split on the other side. Notice that these go over from the outside to the inside of the donut in the same direction, the same way. And these can be actually combined. And here we are, a bisectional bifilar CMC winding, where we have bifilar on one side and bifilar on the other side, so it's bifilar and split. And you can again see the windings coming over the top and to the inside of the core. And then what happens is we tie the whites together on both ends, and we tie the browns together on both ends. And those form the center pin and the ground connections on the input and the output. What this does is it allows you to maximize the number of turns on the core. It spreads the current evenly around the core so that the magnetic properties are spread evenly. You get a very nice tight coupling of the magnetic field formed by the coils into the core. Here you can use pretty good insulation. Very often it's Teflon or PTFE. It's another name for Teflon, which has pretty good insulating properties, typically a couple kilovolts. And with the center open, you could even slip it over a piece of PVC tubing for mounting on various structures in a mast configuration. Other types of CMCs, the snap-on ferrite beads, mix 31. Typically you'll have at least 6 on a piece of coax. And here's an ugly BalUns. 6 turns of 6-inch diameter air core. You'll often see these in older vertical configurations near the base. They recommend that you take some coax and you build an ugly BalUns. These both have limited common mode current suppression capabilities, as we'll discover soon. Couple factoids: they are reversible inputs and outputs. They can be with or without a crossover. The dots on the schematic means the same end of the coil. So keep that in mind whenever looking at any transformer schematics. And you want to keep the winding handedness consistent on the ring. And remember, DC continuity is not the same as RF continuity. You could have an RF that's in open or short, even though the DC continuity tells you opposite. We're talking in the RF domain works completely differently than DC domain. So here's a quick chart of common mode choke power handling budget. So here we have on the left-hand side different size toroids, combination with different size wires, and even different size coax. And we have 3 columns, one for sideband, one for CW, one for digital. Notice that these are derated for the digital and the CW because the duty cycle of on time versus off time is much higher than for sideband. So now let's switch to BalUns and Ununs for transmission line transformers. So the first thing I want to mention is realize that an antenna system is like a mirror stack. The antenna systems are like a series of partial mirrors, each interface determined by an impedance match. Each interface downstream multiplies the system losses. Fixing one does not fix interfaces upstream or downstream, and that's why a rig side tuner will not fix the system. They'll only make your rig be able to tolerate a certain amount of SWR without complaining or without tripping out or shutting down on you. So we must maximize the transparency, or in other words, the impedance match at each interface. So it's a little bit like looking into one of these infinity mirrors. Here's an example of chain losses at frequency. So after the transmission line transformer, you might have a loss of SWR of 2, which is about 11% at your best tuning. With an auto tuner in the system, you might get another 10%. 50 feet of RG8X is another half a dB, another 11.8%. Coax to match the rig. Let's assume we have a perfect match here. So you get 88 or 89% times 90 times 88.2 is 70.5%. You've lost a third of your power. So, and note that ladder line, typically 450 ohms, is low loss, but it changes when wet. So coax is usually recommended, except for more classic antennas, G5RVs and bazookas and such like that, Wyndhams. Now, just to calibrate everybody gets worried about SWR. Oh, my SWR is way up at 1.5. Well, guess what? That is a 4% loss. That's nothing. Now, if you've got a lot of places that are losing 4%, then you got a problem. But even at 2.0, SWR is only 11% loss. So if that's the best you can do, don't sweat it. You're still getting about 90% of your power out onto the antenna. So, a little bit about BalUns versus Ununs. What's the difference? Well, they're both auto transformers. They share a core like a common mode choke. But the balance devices is where the output is balanced across the ground, as you'll see in the schematic of these devices. Whereas an unbalanced device, the output is referenced to the ground. In other words, the input and output grounds are the same. They're shared. So a couple typical impedance ratios is 1:1, 450 ohm, like a dipole, 200 ohms, such as an off-center fed at 33%, gives you 4:1. 9:1 is very popular for off-center feds at the 20% point, or even random wires, and 49:1 up to 64:1 for an end-fed half wave. Typically 4:9:1 is 2450 ohms. You install that between the current choke and the antenna, and the TLTs simply reduce the SWR to get you in range of an auto tuner, typically. Either the rig auto tuner or, even better yet, an auto tuner at the feed point. So, a couple examples. Balanced devices are dipoles, loops, folded antennas, folded dipoles, ladder line tuners. Unbalanced devices are verticals, end feds, off-center feds, G5RV, and coax cable. Unbalanced antennas can cause common mode currents. So now, let's take a look at a half wave at 40 meters. This is a plot of the current along a half wavelength of 40 meters. That's the blue line here. And notice that if we switch up from 40 meters to 20 meters on that same length of wire, we get the red lines. And if we switch up to 15 meters, we get the green lines, these green humps in current. And finally, at 10 meters, we've got the purple line, which are these humps here. Now notice something. On 40 meters, the blue curve, and on 15 meters, the green curve, I have a pretty good current, which will give me a reasonable amount of voltage and an impedance somewhere around 50 ohms, which is a pretty good match. However, on 20 meters and 10 meters, I have zero current and very high voltage. And so I'm not going to get a good match at all. So that's why a half-wave 40-meter dipole works as well on 15. Now, notice all of these curves converge at the ends, at either this end or this end, and that's where you'd have an end-fed half-wave, because very, very low current and very high voltage, voltage divided by current, is resistance, or in RF talk, it's called impedance, and that's why you need a very high ratio TLT. So if we move off from the 50% point in the middle of the physical dipole, we can move off a little bit and get 200 ohms at around, this is at 25% for reference, somewhere around 28%. You get very quickly an increasing impedance of 450 ohms, and at the end you'll get thousands of ohms of impedance for an end-fed half-wave. So another way to look at this is if we take our dipole and we feed it in the center, 50 ohms. As we move the feed point further and further towards the end, we move to higher and higher impedance in kind of an exponential increase. Now, let's take a look at impedance transformer ratios. Why are impedance ratios always a square of a nice integer number? 4 to 1, 9 to 1, 49 to 1, etc. Well, it's very simple. All you have to remember is on a transformer, the output voltage, V2 over V1, that ratio of output voltage to input voltage, is equal to the turns ratio, the output turns versus over the input turns. Now, remember Ohm's law, V equals IR, or R is equal to V over I, which is the same as impedance in the RF world. If we make the turns ratio 2 to 1, all right, N2 to N1 is 2, then V2 is twice V1. But because we have to conserve power, the power on the input equals the power on the output, assuming a perfect transformer, we'll be very close to that. Transformers are pretty efficient these days. Then the current has to drop in half. But because impedance is voltage over current, if we double the voltage and half the current, guess what? We get a 4 times V over I, or impedance Z, and that gives us the square of the turns ratio. So the impedance ratio is always the square of the turns ratio. And that's a very handy thing to know. So now let's take a look at BalUns, or balloons. No, not balloons. Let's take a look at a BalUn. Here it's a 4 to 1 BalUn. And I know it's a BalUn because the input ground is not directly connected to either side of the output. It's somewhere in the middle. And so that immediately tells me it's a balance. I have balanced output versus an unbalanced input. Coax is unbalanced. And BalUns and Ununs, in other words, TLTs typically use mix 43. Sometimes you'll see other mixes, people are experimenting with them, but for the most part, most people have most experience with a mix 43. Let's talk about an Unun. No, not that kind of an Unun, this kind of an Unun, 9 to 1 Unun. Now, let's take a look at the ground. The ground here is shared between the input and the output. That tells me I'm an Unun. Unbalanced input, unbalanced output. A long wire, an off-center fed, end-fed half-wave, whatever. And notice I've got 3 equal length coils. Notice the dots. Okay, they're all on the top of the coil. So they're all on the same end of the toroid, whether it be the counterclockwise end or the clockwise end. And that's how you would hook it up. And so because I have 3 coils on the output versus 1 coil on the input, that's a 3 to 1 turns ratio, which turns out to be a 9 to 1 Unun ratio Unun because it's the square. So a little way of looking at BalUns versus Ununs. BalUns will match balanced device to an unbalanced device. The input is grounded on one side only. The output is taken across the differential signal. It minimizes common mode current, often used to do impedance conversion, and the input ground is never tied to the output ground. Now I want to mention something. You'll very often hear a one-to-one balun. That's a bit of a misnomer because one-to-one is not doing any impedance conversion, and all it's really doing is suppressing common mode current. So it really should be called a CMC and not a one-to-one balun. If it's a different ratio, yeah, it's a balun or an unun. Now, ununs will match unbalanced devices to unbalanced device. It's often used to do impedance conversion, does not minimize common mode current, but it typically has an output at the end of the coil closer to the coax center, and typically has input and output grounds tied together. So now let's take a look at this Smith chart for a second. Smith charts, don't be scared. All this is doing is just a different way of mapping out impedance. That's all you're doing, and helping you map out the impedance translation or conversion from one impedance to another. So first thing to notice is this equator is the pure resistance. So impedances are given by R, the resistance, plus a reactance value, that's plus or minus. If the coordinate that the antenna is sitting at gives you a dot at that frequency north of the equator, north of the resistance line, it's inductive. It's positive reactance is inductive. Negative reactance, it's net capacitive. And this is why if it shows you something capacitive, you have to add an inductor, and vice versa. In the very center is my 50 ohm point. That's my target. That's perfectly balanced and matched to a 50 ohm coax in this case. At the 9 o'clock position, it denotes a pure short. At the 3 o'clock position, it denotes a pure open. And hence, if you're calibrating a nano VNA, you will typically do an OSL calibration. You'll give it an open, you'll see the dot appear here. You'll give it a short, you can see the dot appear here, and then a load, which is a 50 ohm load, you'll see the dot appear here. If you see that, you know you're calibrated. So now let's see how this works. Let's assume we have an off-center fed at 20%. So that we start over here at 450 ohms, heading more and more towards an open. Okay, higher resistances moving towards an open, and it goes up exponentially very quickly here. So this is where 450 would lie. So in a perfect off-center fed with no reactance to it, not a realistic situation, but sometimes not too far off, we want to move the R value, and only the R value, to the center, which is 50 ohms with no reactance. Okay, so guess what? What kind of TLT should we use to fix this? Yes, 450 ohms divided by 50 is 9, therefore a 9-to-1 unon is what we need. So using SimSmith, which is free, and I recommend you all download this because it's a phenomenal tool for doing analysis and modeling. And I'll just make a note here that if you store what's called an S1P or an S2P file, which is the reflected signal off your port 0 of your nano VNA that's used for SWR, or the other channel, the port 1 channel on the nano VNA for through readings of things like filters and other devices that you're measuring the performance through the device as opposed to reflected from the device. You can literally import that to your PC and literally drag and drop it right here, and it'll actually create that antenna, replicate that antenna in SimSmith right here. And so 450 ohms, we've started off here, note it's 450 ohms and 0J ohms of reactance. Again, we start right off about here, and we want to get to here. So if we just did nothing but took a reading, we would notice that it would have an SWR of about 9. Well, guess what? If I have a pure resistance of 450 ohms, SWR is simply the resistance of your device divided by your characteristic 50 ohm impedance, which in this case is 9. So That's exactly what it would show me. Now, this is an ideal case, but in the reality, it's going to be roughly around that number, but it gives you a pretty good idea. This is what it looks like if we add a 9-to-1 unknown, just a 9-to-1 unknown purely. Now, these are circles of equal SWR that I have set up. I've set that up using this, with just a space in between the SWR values I want to plot. So 1.5, 2.0, and 3.0. So I want to see where my 80 meters, 40 meters, 20 meters, 15 meters, and 10 falls at these frequencies, 3.7, space 7, space 14, space 21, space 28. All those 5 bands. And it just naturally falls that everything but 80 meters is already within 3.0, which often is what a auto tuner in a rig can handle. And this is what the SWR chart would look like. Well, here's 3.0, here's 40 meters, 20, 15, and 10. Now, if we add a 150 picofarad capacitor, what it does is it brings that curve and that plot of those points down into the circle. And so more of them are within or close to a 2.0 SWR. All 3, almost 40 meters is almost there. And if we do an SWR mode, look at it, you'll see that they're almost all below 3.0, except for 80 meters up here, and they're more balanced below 3.0. Now, if we add an auto tuner at the feed point, then guess what? We can actually bring more of them closer to the inner circles of SWR and tune for, let's say, 20 meters. We can tune each one and bring each one in right into dead center in an SWR 1.0. And that's what this would look like. At 20 meters, we have a beautiful SWR, and that's how SimSmith works. And we are always adding devices from the antenna to the generator or the rig. And so everything is built from the left to the right. So let's talk a little bit about toroid mixes. We have Mix 31 and Mix 43. Mix 31 is for CMCs, Mix 43 is for TLTs. They do have a slightly different frequency range, and the materials are different. And now they look identical. They're both gray donuts. How would you tell one from the other? Well, Mix 31 actually has a little bit of conductivity to it, whereas Mix 43 is an open. It has infinite resistance. And so that's how you can check. Now, for confusion can happen between ferrites and iron powder. Some people get confused and think that you can use an iron powder core for a CMC or TLT. You cannot. You'll typically see the red or yellow cores. Notice the permeability, the magnetic effectiveness essentially, is orders of magnitude different than the ferrites. And the inductance coefficients are orders of magnitude higher. So iron powder cores are for building compact inductors. That's the main reason. You'll see these in auto tuners, but not for CMCs and TLTs. So let's talk about TLT power handling budget. Again, these are different toroids. This happens to be the ferrite device. It's a very popular device these days. It's taller and has a very thick wall for very good magnetic conductivity. Some combinations of wire with the toroid, and look at the power handling capabilities. So you can take a look at this offline, but again, from sideband to CW to digital, you have to be derating this. So let's take another look at current balance, or CMCs, another way of calling it. And here's a way of a bifilar winding with a crossover, and we have 50 ohm unbalanced, and the output is actually balanced. So that's why it's called a current balun. So yes, you could call it a balun for a 1-to-1, but it's the same thing. It's called a CMC. Now a 4-to-1 balun is wound differently. It's bifilar, and notice that we've stacked the coils by connecting the dotted end of the blue to the undotted end of the red, which is where we feed our input across the red and take the output across the undotted part of the blue to the dotted part of the red. A 4-to-1 unun, again, shares the ground, looks very similar, looks wound in a very similar way, but it's connected differently. My center pin is going to between the coils, and I have a balanced output, and it gives me a 4-to-1 ratio. Why? Because the total number of turns on the output is equal to twice the input turns, and the square of that is 4. Stacked up looking more like this. If you stretch it out and stack it like this, it's a heck of a lot easier to understand. Here's a 9-to-1 unun. Okay, again, 1 coil and then 2 more coils. The output is across all 3 coils. 3-to-1 is 9, and output is 450 ohms impedance. Here's a 49-to-1 unun, and here it's typically I have 3 turns on the primary and 21 turns on the secondary, and that's 7. And that ratio is 7. 7 squared is 49. 49 times 50 is 2450 ohms, and that's the impedance that it wants to see at the antenna. And this is typically how it's wound. It can be wound either together bifilar of the primary with the secondary, the red secondary, or sometimes people will actually twist these together on the primary side and then continue winding it around. It really doesn't make much of a difference. It's just another way to give you that tap for the center pin of your input. Now let's look at a commercial unun, which is an LDG 4-to-1 unun. And a 4-to-1, the output turns would be twice the input turns, wouldn't it? And that would give us 200 ohms. Now, this balun ratio is interesting. We have 2 coils of 2 turns, and then on the outside we have 2 coils of 6 turns. So we have 4 turns on the input primary, 16 turns on the secondary, and so the impedance ratio is 16 over 4 squared, which is 4 squared, which is 16. Now, for reference only, I want to let you know there's another family of TLTs called the voltage TLT. We've been talking about current TLTs all this time, and that's what pretty much everybody uses today. Voltage baluns do exist. They're called Ruthroff baluns. You might see them referred to as such, whereas current baluns are sometimes known as guanella baluns. So it's just historical terminology. Voltage baluns, however, are really not favored. They were built into older devices to accommodate tube outputs and other high-powered tuners of older days, but they have some subtle issues to them that can creep in and would be hard to diagnose. So there's just take a look at that. You can see there's just a few differences, but I want to point out that these are voltage baluns if you happen to see them, okay? And they are not recommended. They are rarely used in practice, whereas current baluns, otherwise known as guanella baluns and ununs, can often provide common mode suppression. And as I said, these voltage baluns are sometimes found at the output of older devices. Now, an interesting animal is the multi-ratio TLT. Could be a balun, could be an unun. And if you go for electrically short antennas that use impedances less than 50 ohms, you could actually transferred or translate the impedance upwards. But most of the time you'll be doing a translation of the impedance downward to your 50 ohms. It gets the radiation resistance or R value of your impedance in the zone for the ATU to handle. Okay, it's very small, light and cheap and easy to build. Can use a rotary switch to select the desired ratio for a band, and you can test it with a VNA with a resistor to simulate the R. So here's one, for example. It's got a, here's the feed point. Here it has a bifilar common mode choke on a mix 31. Here it's got a quad filar winding on a mix 43 ferrite. And then the outputs, here's your ground, and here's your 3 taps. In this case, it's taps for 4 to 1, 9 to 1, and 16 to 1. Okay, so these are just your different taps that you would have. And that's a commercial device that you can buy, or you can build your own. Another thing you could do is you can put taps on the primary. So if you have 2, 3, or 4 windings on your primary and multiple taps on the secondary, you can have a wide variety of ratios that you can create. And here's an example of some different ratios. If I have this number of turns for down conversion from the antenna to the rig side, of this number of turns on the secondary and this number of turns on the primary or the rig side, I can generate a variety of my R values very easily by being able to switch between, or just tap different taps between these 2 ratios. Of course, you can use any number here above you, 12, 13, 14, doesn't matter. And which you can get ratios that are not integer, 3.7. 17.8, whatever you like, you can build it. Now, impedance matching guidelines. Feed the antenna at the appropriate point. Okay, scan the antenna's impedance across that spectrum. Note the resistance values in each band that you want to match. Choose the TLT ratio for an SWR well below 3 for your chosen bands as a kind of a trade-off balance. Use the appropriate TLT type, balun versus an unbalun. Use a tuner at the feed point if the SWR is high because of reactance more likely than the resistance. Isolate the feed line from the antenna, usually, except for maybe an unfed half wave, and use the rig tuner to keep it happy with SWRs below 3. All right, let's look at a TLT example. We want to match a 50 ohm coax to an off-center fed at 20% from the end. Do we use a balun or an unun? Well, the coax is unbalanced and the off-center fed is unbalanced, so unun. We measure the impedance at the feed point at 450 ohms. So 450 divided by 50 is 9 to 1, gives us a turns ratio of 3, and we use a toroid mix 43, and we'll learn how to wind that coil in the Part B section of these presentations, which is the workshop section. And the purpose of an input capacitor is to help bring down the reactance that is part of a TLT in the system. You'll see that if you bring in a reactance on SimSmith, bring in a pure TLT, you'll have some positive reactance, which means slightly inductive. And a capacitor, it will be used to balance that in parallel. So you typically will see people putting a capacitor, typically 100 picofarad capacitor, across the input to a TLT to bring that closer to 50 ohms. So let's talk about measuring a TLT. Turn on my laser. So first thing we do is calibrate with open, short, and load, as we mentioned before. Set the nano VNA to SWR format. Select channel 1 to read the SWR. We'll call this port 1 and port 2. This is the port where it sends a signal out and looks for how much is reflected versus how much continues on to the load. It should be around a 1.0 SWR with a correct load. We can save that with an S1P file, touchstone file, on the nano VNA. and some nano VNAs cannot, but many do. The S1P is port 1, and by the way, the S2P is if we wanted to measure something on a through mode, and that would be an S2P. That can be imported literally by dragging and dropping that from your desktop into SimSmith as the source scan file of your antenna. And then you'd have a scan of your antenna from, say, 3 to 30 megahertz in SimSmith that you can do all kinds of experiments with in simulation rather than in having to mess around with real antennas. So if we look at a 9-to-1 Unon with a 150 picofarad capacitor on the input, but only a 50 ohm load that matches our 50 ohm nano VNA, we'll notice that we're getting SWRs somewhere around 7 to 8-ish, which is pretty close to 9. So that's a pretty good indicator already that we need to have something much higher as a load, higher than 50 ohms. So if we move that to a 440 ohm load, which is two 220 ohm resistors in series, now I get something that in general is well below 2. Here's the 2.0 SWR line, and all of it is below 2, even though it creeps up in higher frequencies, which is pretty typical. And that's because of the frequency response of the ferrite, not for any other reason. Now, where do we want to place the common mode chokes and TLTs? Well, here's our rig, maybe with an optional auto tuner. And if we want to suppress any RFI or any other nearby signals that are not on frequency coming into our rig, we put a common mode choke at the rig end of the coax. And then we bring this feed line up from the shack, and the first thing we do is put another choke there. This is one we always want to put there, which is why this is dotted. It's optional, but this is solid. It is always desirable to have a choke at the end where the feed line meets the antenna. You might have an ATU at the antenna, and then you'd have your BalUns or Ununs here to your antenna. In this case, it would be a vertical with a ground, a radial, or a counterpoise, or it might be 2 halves of an antenna, 2 blocks of blue here for a dipole, folded dipole, or whatnot, something more balanced. So, this presentation in PDF mode is available for your perusal offline with this QR code, and this QR code will bring you to my TennaTalk series, which is on my Antenna Whisperer YouTube channel, which is a very comprehensive set of tutorials that'll take you from very basic concepts, dispel a lot of myths, give you a tremendous amount of insight, take you all the way through nano VNA, analysis of your antenna system to modeling with EasyNet and SimSmith and a whole bunch of other great topics. And this podcast actually continues the TennaTalk series. So with that, I hope you have gained something here, and I hope I've demystified some things about BalUns, Ununs, and common mode chokes. And with that, I'll say 7-3 and hope to see you up on TennaTalk. Bye-bye.